The Interested Reader podcast is about exploring the world beyond the textbook. We'll cover many lessons in math, physics, and astronomy, and then delve into the mysteries of the universe. Physics is fun, people just don't know it, and I want to change that. I want to spark your curiosity about the world around you and ignite your passion for exploring and questioning. I'm your host, Sarah Tyke. Come with me and let's take a random walk into the world reserved for the interested reader. Hi everyone. In today's lesson, we are going to be talking about projectile motion. And if you'll remember from a previous lesson, we talked about motion in one dimension along either the x or the y axis. And today we're going to be talking about motion in both the x and the y direction. So from last time, we have our equations of motion here in one dimension. We have our x direction and our y direction. And we're going to essentially be solving these equations for time to remove that component, and then we will be combining them and get our motion in x and y directions. So as always, we're going to start with our coordinate system. Our y-axis will always be positive up and down. And our x-axis will always be positive to the right. Y will be positive up. X will be positive to the right. So what we're going to do is, in projectile motion, we have a projectile that launches at some angle to the x-axis. We're going to call that theta. And it's going to have some initial velocity v0. And then it launches, it goes on its way, and it comes back down, and it eventually crosses the x-axis again. So when it crosses the x-axis again, when it kind of ends its trajectory back at the x-axis, that distance from the origin to its landing point is going to be called the range r. And then at the top of its trajectory up here, as we'll see in a little bit, its velocity is going to be 0 when it's at the top of trajectory. So we're going to talk about our vector notation. If you also remember from one of our lessons, we talked about unit vectors. So we're going to write our velocity, our initial velocity, as v0 x component in the I hat direction plus v0 y component in the j hat direction. So again, I hat, j hat are our unit vectors to just let us know that we're along the x or the y axis. Now if we expand our angle theta in our diagram there, we would have our velocity is our vector here, our x-axis, and then our angle theta. So v0 x and v0 y are the x and y components of this vector v0. I'm going to write this a little bit clearer. So we have our vector v0, and then we have an x component and a y component. And again, our angle theta is relative to the x-axis. So if you remember our mnemonic when we talked about vectors, SOHCAHTOA. I don't know if any of you remember this from trig classes. So sine is the opposite side over the hypotenuse, cosine is the adjacent side over the hypotenuse, and tangent is the opposite side over the adjacent side. So we're going to write our v0 x component. Since that is the adjacent side, we're going to be talking about cosine, and the hypotenuse is going to be v0. So we're going to have v naught times cosine of theta. And our y component is going to be v naught y. Since we're talking about the opposite side from our angle, it's going to be the sine. So v naught sine theta. So a couple things to remember when we're talking about projectile motion in this case is that the position vector and the velocity vector are constantly changing throughout its trajectory, but the acceleration is going to be constant, and it's always going to be directed downward. So in all of our cases, we're going to be talking about acceleration due to gravity only. So we're not going to be accelerating an object downward. It's only going to be acting under gravity, and that will be constant. So horizontal and vertical motion are going to be independent of each other. So neither of their motions will affect each other, and that's why we can break down our equations into our two component parts, our x and our y, because they are independent. And there's an example that you'll see in most textbooks about two balls being dropped at the same time. One is just free fall dropped and the other's fired horizontally. And the question is, which one hits the ground first? The answer is that both of them hit the ground at the same time, because each is under the acceleration due to gravity only in the y direction. So both of them have the same acceleration in the y direction. They get pulled to Earth at the exact same rate, which is just gravity. All right, so now that we have our v naught x and y components, we're going to start solving our equations. And we're going to start with horizontal motion, because this one's pretty easy. So I'm going to erase what we've got here. So horizontal motion would just be our x component. So in this case, this means that our acceleration in the x direction is 0, because we have, like I said, no acceleration in the x direction. So what this means is that our x component, v naught x, is unchanged. And if you recall from last time, we had our displacement equation, x minus x naught equals v naught t plus 1/2 at squared. So in this case, we're going to substitute our v naught is going to be v naught x, since we're only talking about horizontal motion. And acceleration in this equation is going to be 0. There's no acceleration. We're not changing speed. So that gives us x minus x naught is equal to v naught x component times t. And from before, we said that v naught x was equal to v naught cosine theta. So we're just going to substitute that into our v naught x in our equation. And we get x minus x naught is equal to v naught cosine theta times t. So that is going to be one of our primary equations throughout this lesson. I'm just going to call that equation 1. So if you have a chance, if you're following along, you can write this down if you need to. But that will be our first equation, and we're going to now talk about vertical motion. So vertical motion will be in the y direction. So we're going to take our previous equations of motion for the y direction, and in this case we're going to start substituting. Our v naught is going to be v naught y, our y component. And again, we're not going to have any v naught x because we're talking about just the vertical motion, so there won't be any x component to velocity. And we just said in our previous discussion here that v naught y is equal to v naught sine theta. So recall we had a previous equation, y minus y naught was equal to v naught t minus 1/2 gt squared. So I'm just going to start substituting in our v naught y. So in our first equations that we talked about in the one dimension, this v naught y was just simply v naught, but now we're separating it, so it's going to be v naught t. And then we can just put our v naught y, we'll substitute that in, and we'll get y minus y naught is equal to v naught sine theta times t minus 1/2 gt squared. So now what we're going to do is we are going to take, this is going to be our equation 2. Let me just separate that off. This is equation 2. And we also know that velocity is equal to v naught minus gt from our previous discussion in one dimension. So turning that into our y component version, we would have vy is equal to v naught y minus gt. And again, I'm going to substitute v naught y with our sine expression. So v naught y is equal to v naught sine theta minus gt. I'm going to call that equation 3. Alright, so we're going to do one more equation to get our kind of our final set. And I'm going to have to erase all of this, guys, sorry. Hopefully, if you're actually following along, hopefully you got that down. So recall from a previous discussion in one dimension that we have v squared is equal to v naught squared minus 2g times y minus y naught. So I'm just going to put in our v naught is going to become v naught y squared minus 2g y minus y naught. And then again, we're going to substitute in here. V naught y is we're going to use our sine expression, so that becomes v naught sine theta quantity squared minus 2g times y minus y naught. So that is going to be our expression simply for v squared. And that would be in our y direction. So in the y direction, when you have a projectile, you toss it up in the air. That's your initial v naught in the y direction. It's going to travel up in the air. It's going to come to the top of its trajectory, and then it's going to start coming back down. At the top of its trajectory is where we have velocity equals 0. So when you start solving these problems and they say, how high does something go? It's going to reach its maximum height when velocity is equal to 0. So that's how you'd go about solving those problems. And we will talk about that at some later time. I think for now that's all we're going to do. Next time we'll talk about the equation of the trajectory. So when we talked about, we had our x and y axis, and we actually have our projectile going up and coming to its peak, coming back down to the x-axis. We're going to talk about the equation of this trajectory and what does it look like. And then we'll also talk about the range of motion, that horizontal distance that actually does travel along that x-axis. So next time we'll be talking about equation of trajectory and the range r. So let me just go ahead and recap our equations. We came up with 4 of them. So our first equation was x minus x naught equals v naught cosine theta t. Equation 2 was y minus y naught equals v naught sine theta times t minus 1/2 gt squared. Equation 3 was v in the y direction is equal to v naught sine theta minus gt. And our last equation was v in the y direction squared equals v naught sine theta quantity squared minus 2g times y minus y naught. So those are our 4 equations for projectile motion. And again, next time we will be talking about the equation of the projectile's trajectory and the range r that it travels along the x-axis. All right, guys, if you have any questions, again, make sure you contact me. And thanks for listening, and I will see you next time. Hi, everyone. Welcome to the Interested Reader podcast. I know it's been a while since the last episode, and I know these episodes are taking longer and longer for me to finish and post. It was supposed to be every other Friday, and I don't know if I've ever actually met that deadline. But part of the reason is because I'm also trying to launch a business kind of based around the podcast. It's going to be kind of like tutoring, teaching. So I'm trying to write course material and try to figure out how to get this, business launched so I can actually do something useful. Not that the podcast isn't useful. I love doing it. But I also like creating content like workbooks and worksheets. And so it's just a really fun thing for me to do. And I would like to, at some point turn into a business where I could actually do that full time rather than just trying to squeeze in, a couple hours when I have free time. So eventually the goal is to be able to quit my day job. Isn't that everyone's dream? And then actually be doing something that I really love doing. So I'm spending a lot of time working on that. So the podcast is kind of taking a bit of a backseat. So it might even be, I hate to say once a month that I'm going to be doing this, but it might actually go that route for now. And then I'm also trying to do, the lesson portion is actually going to end up being a separate series. I'm going to put the lessons with the podcast. I still want that to be one contained thing. So if you actually are a podcast listener, you don't have to go to the website and look at this different section, this different series of videos to get the lessons. But those lessons are supposed to be, this kind of like the business side. It's going to be a series called Physics Explained. And I'm really trying to keep those very short to like no more than 10 minutes. And I know that when I get into the podcast, when we're doing the lessons here, as you all have probably noticed, they kind of go on. They kind of stretch into 15, 20 minutes. And for this video series that I want for part of my business, I'm really trying to keep them at the 5 to 10 range, maybe even like 5 to 7 minutes. Keep them really short. So I'm almost having to re-record the lessons because for the podcast, I want it to be a little bit longer, more in depth. Unless you guys really are hating that, then let me know so I can change it. But so anyway, so the business part is just taking up a little bit more of my time. So the podcast is taking a little bit longer to get out. So, but we'll just keep, getting through it. And I apologize if it takes a little bit longer to get these out, but I am working on other things. And if you go check out the website, I'm trying to also update that and make that a little bit cooler. One thing that I've done that I'm pretty proud of, if you're watching here, I'm just going to click on the website. Shameless promotion here. So if you go on the home page here, instead of the navigation bar, I've got this one link called Civilian Station. And then this is where you can find all of the other categories. So it's kind of the directory for the whole website. So I've got the blog, the section called Level Up is where you'll go for lessons and courses, quizzes once I get all that content made, podcast link, contact form, the shop, and the resource page right now doesn't have a link to it, but eventually that will be links to a lot of the websites that we use during the podcast, books, anything interesting that I've found in the podcast will go in the resource section. And for the interested reader, the name Civilian Station actually comes from a comedian, Nate Bargatze, and I don't have a link here showing, but he has a podcast called the Nateland Podcast, and they were talking about civilization, and he just garbled the words and said Civilian Station, and I just thought it was a great name for this particular website. So hopefully, again, I don't get any sort of copyright infringement. I don't think they would care. Not like they even noticed that I'm here. But the Nateland Podcast is an awesome podcast if you love family-friendly comedy. That's one of my favorite things, is that everybody on his show, they're all clean comics. So I never have to worry about, oh my gosh, is my son going to walk in and hear something weird? No, it's all clean. It's all for all ages. And all the guys on that show are super funny. So the Nateland Podcast, check it out. I don't get paid at all for promoting that. I just really love the podcast. It's one of my favorite things. And I've been falling behind on that too because I feel like I don't have time to do anything. May have something to do with having a 19-month-old running around the house. I don't know. All right, so that's kind of an update on what we're doing here and how things are going to probably slow down in the podcast a little bit, but I'm also trying to get some other cool things going for you guys. So again, let me know if you have any questions, suggestions, comments. And if you go to the Civilian Station on the website, again, you can scroll down to the contact page here with the big Don't Panic icon. Also, Don't Panic is a reference to the Hitchhiker's Guide to the Galaxy. A really fun book if you are interested in really fun sci-fi. The movies weren't great, so I wouldn't waste my time with those. Book was awesome. All right, so getting into today's topic, we're going to talk about my favorite star, probably everyone's favorite, I would hope, the sun. So obviously it's the closest one, and I did not bring up a page that I need to, because you can't talk about the sun without going to the Soho Observatory. If I can type here, I'll put it in, but because the Soho Observatory is the Solar and Heliospheric Observatory, and all they do is the sun. That's the only thing that this website is dedicated to, is the sun, and everything imaginable about it in every wavelength. So you can go, and they've got here's the sun now. They've got sunspot trackers. They've got space weather, solar wind. They've got just like everything that you could want to know about the sun. So this is a really good place if you want to go and look at daily sunspots. You just want to know what's going on with our star. And you can go and look at, I'm just going to go to the gallery, because this is where they got the really cool things. So they take pictures of the sun in all these different wavelengths. Oops. So you can see they've got a couple. They don't really say what they are easily. Anything that's in the orange is going to be your visible light, and then I think they do X-ray, UV. This is one of my favorite things here. Looking at the, so the MDI sunspot is kind of where you want to go if you're going to look for sunspots, because that's the visible light. So when I was teaching astronomy, we used to always go to this website when we did the units about the sun, because the picture is so awesome. I mean, I love this. This is the actual picture of the sun here in visible light. Obviously, don't look at the sun. I don't know if they sell these in stores regularly. I have never seen them except when there's a solar eclipse coming up, and then they'll sell the solar eclipse viewing sunglasses. You can get them online, obviously, whenever you want, but when they have an eclipse coming up, a lot of the stores start carrying them. So those are super fun. I always like to have a pair just hanging around. You have to be careful because I think they do expire, I think, in 3 to 5 years, I think it's 3 years. Because the film in the lens can break down over time, so just make sure that if you're going to keep a pair around that it's not for too long, because that film can break down and then it's not as effective and you can do some serious damage if it's not 100% effective film in those glasses. All those are on, these instructions are on the glasses, so just make sure you're reading carefully before you start looking at the sun with any sort of medium. So you put a filter on your telescope and you can look at the sun, and it looks just like this. So you'll see that the dark splotches all over the sun they're sunspots, and those are areas of magnetic fields. And we're going to get to all this in the podcast today, but so this is what the sun would look like, on any kind of given day. This nice bright orangey color. Depending on where we're at with the solar cycle, you may see more or less sunspots. So when I was teaching in astronomy, we used to do this, where we would put the filter on the sun, on the telescope, so the kids could look through the telescope at the sun, and you would actually see this. I mean, you could see the sunspots on the sun through one of our telescopes, and I don't think it was that big a telescope. I think it was maybe an 8 or 10 inch. Just, I mean, kind of standard for, at least for a school or college observatory. Okay, so that's the SOHO website. So if you're interested in the sun, make sure you go check out the SOHO Observatory, and that's just soho.nascom.nasa.gov. Just do a search for SOHO Observatory and you'll get it. If you search for just SOHO, you might get SOHO, New York. So let's see what else we got here. They've got a whole bunch of stuff. So they've got images of the corona, which is fun. But yeah, so we'll get to all this throughout the podcast here. All right, so we'll just do a few basics about the sun, just to kind of get an introduction to. Oh, sorry, all my stuff got mixed up. So, just the basics. Obviously, the sun is a star at the center of our solar system. And I think we kind of talked about the spectral class of it when we talked about stellar evolution. It's about 93 million miles away from the Earth, and that distance of 93 million miles, the distance between the sun and the Earth, is defined as 1 astronomical unit, or 1 AU. And light takes about 8 minutes from the sun to the Earth. So if something happens on the sun, whether it's a flare or the magnetic fields, the sunspots, it happens on the sun, and about 8 minutes later, we know about it on Earth. So the spectral classification, we talked a little bit about this last time during our stellar evolution episode. It is a G2-5 or G2V star. The V is the luminosity classification done in Roman numerals. So the G2 aspect, again, is, here's our stellar classification, main sequence stars. So here we got the G type star. If you're watching, it's kind of, it's our classes of the O, B, A, F, G, K, M. And if you remember, the mnemonic that we used was, "Oh, be a fine guy, kiss me." Or girl. So here we are with our G star. Temperature 4,900 to 5,700 Kelvin. It's about 7.6% of all stars, all known stars, are G-type stars. So it's kind of, the color range is kind of this yellow, whitish color. kind of just mid-range, just kind of an average, medium kind of star. And then in this picture that we're looking at here, the rainbow spectrum next to it is the spectrum that we use to determine how many or what kinds of elements are being produced in the star. So you have, this is in the visible range, from red to violet. And then wherever you see these dark lines, it didn't help at all. The dark lines are absorption lines, and each element will absorb light at a very specific frequency. So when you see a dark line, it means there's an element there absorbing light. So then we can tell that there's oxygen, sodium, hydrogen, whatever there might be. That's all shown up in this spectrum. We'll talk a little bit more about that later too. So that's its spectral classification. The luminosity class that I mentioned is class 5. So we'll just scroll here a little bit. Here's some more, that's the same chart basically that I just looked at. This is all just a Wikipedia page. So here's the luminosity class. So it goes from 1 to 5 with Roman numerals, and then you got these subclasses like 1A, 1B. So your 1As are your hypergiants. Like they give some examples here. So Cygnus, that's in the Cygnus is the constellation the Swan, and Cygnus OB2 number 12 is the star that's a hypergiant, which would be fun to look at here. Oh, that's not a very good picture of it. So then class 1A supergiants, 1AB intermediate sized luminous supergiant. So it's just a classification, and 5 is way down here at the main sequence stars or dwarfs. So the sun is actually considered to be a dwarf star. Okay, so the next thing, okay, so we got our spectral class, we got our luminosity class. The next is our magnitude. So magnitude's a little bit, there's two different kinds we talk about. We talk about apparent or visual magnitude, and that's just when you look at the sky, how bright is the star on the sky. That is its apparent or visual magnitude. We denote it with a lowercase m. The absolute magnitude is if you were to take the star and move it to a distance of, oh, I'm going to get this wrong. You put them all at the same distance, and I don't remember where that distance is. I'm sorry about this, guys. Okay, so all the stars get put at the same distance from Earth. And like I said, I don't remember where that distance is. So the apparent magnitude of the sun is minus 26.4. And the smaller the number, the brighter it is. So the negative numbers are obviously very bright because they're, smaller number. Minus 26.7 is what the sun is. So you look at the sky, the sun is up there. That's its apparent magnitude, minus 26.7. Its absolute magnitude, if you put it at the standard distance with all the other stars, would be a 4.83. So that's, I think, right around the edge of the naked eye. The naked eye can see down to approximately 4.5. So the sun would be just a little bit dimmer than naked eye limit when it's at the standard distance for its absolute magnitude. So just for some comparisons, when we talk about the apparent magnitude, so these would be, as you look at the night sky, how the stars just appear as we look at them. How bright are they when we just stand in our yard and look? So Sirius is considered it's the brightest star visually, and that has a magnitude, apparent magnitude, of minus 1.5. And that is it's also called the dog star because it is in the constellation of Canis Major. The full moon is minus 12.6. Polaris is the North Star. It's always the one, hey, follow the North Star if you ever get lost. Well, its magnitude is plus 2. So to me, Polaris isn't actually all that bright. I was kind of shocked when I first started taking astronomy courses and I found out which star was Polaris, because I'm like, I thought that's supposed to be the guiding star. Like, you're supposed to find this thing. If you're lost, you can find the North Star. It's like, well, it's so dim. I mean, how do you find it? The good thing about Polaris, though, is that there aren't really any other stars in the area of it. So if you can find it, So as you're looking at you find the Big Dipper. I think most of us know what that is. And the bucket has 4 stars. And you take those 2 bottom stars of the bucket and just draw a straight line and continue that straight line, and the next star you come to will be Polaris. And it's not very bright, but there aren't any other stars in the area that you can see, with the naked eye. So Betelgeuse is in the constellation of Orion. I think we talked a little bit about that one last time as well. So as you're looking at Orion, he's got the 4 bright stars. It's the upper left star, kind of the shoulder of Orion. That is a plus 0.45, and that one's pretty bright. Aldebaran is the bullseye, so if you can find the constellation of Taurus, Aldebaran is noticeably red as well. So the eye of the bull, positive 0.85. And then we said the naked eye limit is approximately 4.5, and the Hubble telescope can see to approximately positive 30. So Hubble's reaching out there. Okay, those are just some comparisons for how bright things are. So sun is very bright. In case you didn't know, the sun is very bright, and don't look at it. Unless you have those sunglasses. Which is really cool. I love those things. If I hadn't said it. Okay, so we talked about the sun being a main sequence star. I think we mentioned this last time. So main sequence means that it is in a state of hydrostatic equilibrium, and it's burning hydrogen in the center of its core. And this nuclear fusion is taking place, and it's balancing the inward gravitational collapse of the outer parts of the star. So gravity wants to pull all that material into the center of the star, but the nuclear fusion going on in the center produces enough pressure to keep all of that material from collapsing in. And so we just kind of sit in a state of balance when you're on the main sequence. So here on the screen, if you're watching, I've got just a reminder. This is the Hertzsprung-Russell diagram, or the HR diagram. So again, we go on the x-axis is the spectral type O to K, or M. O's are the hottest stars, M's are the dimmest and coolest. And then kind of through the middle of the diagram, we have our main sequence. And here's the sun, kind of right in the middle of the main sequence. So once that fusion stops in the center, once we start going, we exhausted all the hydrogen to fuse, then the sun will actually expand into a red giant. So it's going to kind of go over to the right on the HR diagram. So due to its mass, the sun will eventually become the red giant and then collapse into a white dwarf. And we talked about that with our stellar evolution charts. I'll kind of show that again. The stellar evolution all depends on the starting mass of the star. So we talked about this stellar evolution chart last time from the Chandra website. So you've got the same size as the sun, your sun-like star. You've got if your starting mass is much larger than the sun or much smaller than the sun, you've got these different paths. So your sun-like star will eventually become a red giant, and then when those outer shells of the red giant get blown off, it becomes planetary nebula, and then that inner remnant will collapse into a white dwarf. And then if that white dwarf happens to accumulate some mass and become more than 1.4 solar masses, then it can go into a type 1a supernova. So that's kind of the fate of our sun. It might not go into the supernova unless it can accumulate some more mass as a white dwarf. Usually that happens when you're in a binary system. And the sun is not in a binary system, which is kind of strange. Most stars are. There is speculation that there's another planet or another star that is the binary companion to our sun. We just don't see it. Its orbit is on such a long period that we just don't see it in our lifetimes. But there is some wobble to some of the outer planets that make people think that there's something else out there that's affecting them gravitationally. But it hasn't been conclusively proven. And I want to get into this later, but we'll talk about probably more like the electric theory of the universe rather than the gravitational theory. Okay, so that's our stellar evolution. That's kind of the fate of the sun, what's going to happen to it. So just some basics as far as the physical characteristics, the size and the mass of it. I don't think I put this in. Here's some comparisons here. So the diameter of the sun is 865,400 miles. So that's 109 Earths lined up. So, and you could fit approximately within the whole sphere of the sun, you could fit about 1.3 million Earths inside the sun. And Betelgeuse, so that's that star in Orion, has a diameter that's about 760 times the size of the sun. So it's about 1.5 billion kilometers. And within Betelgeuse, as a sphere, you could fit approximately 1.2 billion suns. So you've got 1.3 million Earths inside the sun, and then 1.2 billion suns inside Betelgeuse. And so on this picture that we're looking at on the screen here, it looks like they're kind of different spheres, almost like bowling balls. But so Betelgeuse is this one of the two larger ones on the left. And then the sun, you can barely even see it here, is this tiny little, like pea-sized not even a pea-sized object here. It's like a little grain of like sand or something. I mean, it's tiny compared to Betelgeuse. So now on this chart, the next one next to the sun is Sirius. So that's the star that's, the brightest visually. Pollux we got here, Arcturus. Rigel is this bluish white one here. That's also in Orion. Here's Aldebaran, our bullseye. So you can see like down here's the sun with this little, sand grain-sized object. And then Aldebaran, the bullseye, is over here, so it's quite a bit bigger, baseball size. And then the big one in the back is Antares, which I think is in Scorpio. I think. So the mass of the sun is just about 2 times 10 to the 30 kilograms. And that's 332,950 Earths. So this thing is, it's a really, you think about how many Earths are fitting into this thing. 109 Earths across, almost 1.5 million Earths inside the sun. And you're like, this thing is huge. This is a gigantic object. And it is, but now look at it compared to just some other kind of standard stars are in the area. Sirius is on the smaller size, and it's it's got to be 2 or 3 times the size of the sun. Betelgeuse, look how huge that is. Look how huge Antares is. So for as gigantic as the sun is, it's just this tiny little pea-sized object floating around in the universe compared to all these other stars. So if the sun were the size of a basketball, Earth would be about 2 millimeters in diameter, and I think that's about the size of one of those little bumps on a basketball. So you got the sun as your basketball, you got your Earth as like one of those little bumps on the basketball, and then take that bump and place it about 25 miles away, and that would be the scale of our solar system. It's just, to me, it's incomprehensible. Like, how can it be? How can that work? Because the sun is at just the right distance from the Earth so that we don't get scorched up like Venus or Mercury, and we don't freeze to death like Mars. Although, there is speculation that Mars had an atmosphere, and if it did have its atmosphere back, then you could live on it. But the Earth is at just this right distance so that everything kind of works. So we've got our liquid water, we've got warmth, but it's not too hot, not too cold. We've got liquid water. It just seems, again, kind of, to me, it's just like incomprehensible that this all worked out. And that the sun isn't some huge supergiant that's going to burn up all the planets. And that it doesn't have a binary companion whose tidal forces, tear the planets apart over time. Because that's a big problem when you have binary systems, is that those interacting tidal forces, the gravitational forces between those two stars, make it almost impossible for planets to exist because they'll just get pulled apart. So those are just kind of the basics of the size of it. So as far as the composition and the structure, what is the sun made of? I think I got one more comparison chart here. Yeah. So this is just kind of this has more stars in it, just different series of dots. So again, here's Betelgeuse, one of the main players here. So this one kind of has it backwards from that other chart here. Because in this chart, Antares is bigger than Betelgeuse. And then on this chart, it's kind of the other way around. Betelgeuse is bigger than Antares. So I'll have to look that up for you guys, figure out which one is right. So here's Polaris, our North Star, is way over here in the little left corner. And the sun is here in the center of this picture, if you're watching. But it doesn't even get a dot. It's so small that you can't even represent it with a dot on this picture. So that's kind of cool. Trying to look at what else we got here that you guys would know. Here's Rigel up here kind of in the center. Who else have we talked about here? I thought they had Sirius on here. I probably can't read it. Here's Pollux. We talk about Castor and Pollux. Those are the twin stars of Gemini. So, yeah, I mean, it's incredible how big the sun is to us, yet, cosmically, it's nothing. It's tiny. It doesn't even register on the comparison charts. All right, so what is it made out of? So, it's mostly hydrogen. We got about 74% hydrogen, 24% helium, and 2% other elements like carbon, oxygen, neon. And then the center of the core is iron, and that's included in that. I'm sorry, it's not iron. Iron's out in the other parts of it. The center should just be hydrogen. It will become iron eventually. I think some of these got kind of out of order. This pictures I'm showing here. So this is kind of a cutaway of what the star looks like. So here we've got the core in the very center. You've got a radiative zone, convective zone, a chromosphere. Whoops. Now I've done it. Chromosphere, photosphere, and then this corona is way out here in space. So we measure the composition, as I said, by studying the spectrum and those absorption lines. So how do we know that there's hydrogen? How do we know there's oxygen and carbon? That all comes from the spectrum here. So this is the sun's spectrum. The color band is the visual part of the spectrum. And then the black line beneath it is just a graph of intensity versus wavelength. So you got wavelength on the x-axis from 3,000 to 7,000 angstroms, I believe. And then intensity increases up the y-axis. So if the sun didn't have any elements in it, if it was just what they call a black box radiator, this line in this lower part of the graph here would be perfectly smooth. So a black box is just something that radiates exactly perfectly. As much energy as you put into it, it radiates out. It's the theoretical construct where everything is perfect and it radiates exactly perfectly. However much energy you put into it is exactly how much is coming out. So that's just kind of the model that we use. That's sort of the ideal, the standard that you compare things to. So this line would be smooth if the sun was a black box radiator. Obviously it isn't. You have all these different jagged pieces to it. You have these really strong dips in that line, in that spectrum. And those strong dips, if you look above in the colored spectrum, correspond to really wide absorption bands. So this one way over in the right, around 6,500 angstroms. If you look above it in the rainbow type spectrum up here, it has a really wide dark band at H alpha. So that's a hydrogen alpha line. So because we know that, or we can see that there's this absorption line at 6,500, we know that that element is present, that H alpha. It's all hydrogen, but there's just different levels of it depending, I think, on how it's ionized. And this is just for hydrogen because we've got hydrogen beta, gamma, and delta. I believe that is over there. So that's how we tell what elements are in a star. And we know where the elements, what wavelength they absorb, because in the lab we can test it out. We can put a gas in front of a hydrogen gas source, put some sort of gas in front of it, let the light come through and get absorbed, and then we can see at what wavelength is that hydrogen being absorbed. This was a really fun lab to do in the physics labs when I was teaching those. So that's how we determine what elements are in stars. And I used to do this as an undergrad for one of my projects, it's just a senior project, was to analyze the spectra of stars, and I loved looking at these spectra and where all the absorption lines were, because it's just like clockwork. I mean, you can see exactly where, when you get used to it, you see, oh, I knew these two lines together are always going to be your sodium HK lines, and you see them throughout different stars, and you just get to the point where you're just looking like it's just a signature, and you see it, and you're like, oh, there's sodium HK, there's your hydrogen alpha, and it was just really fun. I mean, it's just, I don't know. I guess because I'm nerdy enough to love that sort of stuff, but it was so cool. So that's our spectrum, and we'll go back to our, here's our breakdown of the solar structure. So in the core is about 25% of the radius. So it goes from the center out to about 25% of the radius of the star. And this is where all of our nuclear fusion is taking place, is in the core. That's where we're fusing hydrogen into helium through the proton-proton chain. And that will continue for about 5 billion years. 5 billion more years. And the temperature in the core is approximately 15 million Kelvin. It's pretty hot. So the proton-proton chain occurs about 9 times 10 to the 37 times per second. And that nuclear fusion is releasing energy at the rate of about 9 times 10 to the 10 megatons of TNT every second. So every second you're releasing billions of megatons of TNT explosions in the core of the sun. Now, a lot of that energy doesn't actually escape. It kind of ends up getting trapped in all these different zones and doesn't actually make its way out to the surface of the sun. So next after the core is the radiative zone, and this is the thickest layer, and it extends out to about 0.7 solar radii, so you're getting about 75% of the way to the surface when you get to the edge of the radiative zone. At this point, energy transfer is through thermal radiation, and the temperature drops to about 2 million Kelvin. So we start at 15 million. By the time we get to the radiative zone, it's about 2 million. And then we get to the convective zone, which pretty much goes out to the center, or to the surface of the star. It's not dense enough for the radiative heat transfer, so at this point convection takes over. So convection is where you have a massive plasma that's heated farther down in the radiative zone, and the mass expands because it's hotter and it's being heated, so it becomes less dense. It rises up to the surface, it cools off, and as it cools it condenses and then sinks back down into that convective zone, the radiative zone, and then the process happens again. It heats up, rises to the surface, cools off, sinks back down. And this actually happens with kind of set masses of plasma. And as these masses are moving up and down, it kind of produces these currents, and it's in effect called solar granulation, which we see in a picture here, which actually to me just looks like a bunch of corn kernels. But each of those, what looks like kind of like a corn kernel, is actually a mass of plasma. And I believe it's hundreds, if not thousands, of miles across. So that's the surface of the sun. It's a very close-up view of the surface of the sun. And those are all individual masses of plasma that are rising and sinking as they get hot and cold. So that's called granulation. All right, so back to our structure diagram. So there's a zone in here called the tachocline. It's between the radiative and the convective zones. And that is an area where there's a very sharp change between the radiative and the convective zone. And it's thought that the sun's magnetic field is kind of generated in this area because of that sharp change. The sun is rotating as well. It's undergoing differential rotation. So the middle part rotates faster than the upper parts. And that is what kind of causes the magnetic fields to kind of get twisted and kind of tangled up, and then they erupt in solar flares, which we'll get to in a little bit. So outside, at the surface of the sun, by now the temperatures cool down to 5,700 Kelvin. So we went from 15 million in the center down to about 5,700 at the surface. So once we get to the surface, we've got the photosphere, which that's the visible part, so that's that orangey part that you see. The photons that are produced in the photosphere escape and become what we see as sunlight. And the photosphere can range anywhere from a few tens of kilometers to a few hundreds of kilometers thick. And the sun spectrum comes from the photosphere. So that rainbow spectrum that we saw with the absorption lines, all of this is taking place in the photosphere. So that's kind of what we see when we see the sun. We don't really see what's going on in the core and those other zones. It's a lot of theory. And in fact, there's a thing called a helium flash that happens when stars are done with their hydrogen in the center. It's called a helium flash. And I know at one point I asked my professor, well, does the star brighten? Do we see, what happens when we see this? Does it actually, how bright does it get with this flash? And they're like, well, we don't really see it. And I'm like, oh, so how do we know what happens? I'm like, well, it's kind of just theory. We think it does. And I know there's reasons for their theories, and they have usually something to back it up. But it was just kind of disappointing because I was like, oh, so we don't really see anything. We don't really see the helium flash, but it's got this cool name. And I think for a lot of people, that's kind of what astronomy does. It is kind of a disappointment because all of those pictures that you see as Hubble, they don't normally get taken in color pictures. I think maybe now they do. I think James Webb might actually take visual color pictures. Hubble has a camera that does, but a lot of the pictures that you see are all false color. They come back from the instruments as black and white, and then in a lab somebody puts color to them. And you have to take 3 or 4 different pictures through different wavelengths and different filters, and then they put them all together in the lab as kind of post-processing. So you're kind of like, oh, so we don't really see it like that. But the picture, the false color, it's not just somebody's on a whim that they're doing it. There are reasons why they color things the way they do, but I was always sure that every image you saw was just like somebody going out there with a camera and snapping a picture, and that's what it would look like, but that's just not how it is. And a lot of it's because a lot of things that happen in space don't happen in the visible spectrum. We have a very narrow band that we can see. A lot of stuff takes place in ultraviolet and infrared and X-ray. So we have to use different filters, and you just can't see it, so you have to put some other color to it. Okay, so that's our spectrum. So after the photosphere, we come to the chromosphere, and that's about 200 kilometers thick. And the chromosphere gets its name because when there's an eclipse, you can see a color flash at the start and the end of the solar eclipse, and that color is chromo in Greek, I believe. So that's how it got its name, chromosphere, because it's a colored flash when you see a total solar eclipse. So at this point, the temperature starts to increase. Now we're going to increase to about 20,000 Kelvin. So we went from 5,000 at the surface to 20,000 in the chromosphere. And then the next we come to is the corona. And the corona you can't see except during an eclipse. And that's the most outer layer of the sun's atmosphere. And its temperature goes up to, on average, 1 to 2 million Kelvin, but can go as high as 20 million. And no one really knows why this happens. The speculation is that the magnetic reconnection from sunspots on the surface basically sends these heat bombs, or these packets of heated material, into space. It ejects these packets of hot material, and then they kind of explode, they diffuse, and then they heat up the space around the sun in the corona. But no one's actually sure yet. And the solar wind is produced in the corona, and the solar wind is what will carry particles from the sun to the earth. And that can cause, I didn't get into this right now, but there's a solar neutrino problem. So neutrinos are produced by these nuclear reactions, but there's not as many detected as there should be given the nuclear reactions that are occurring in the sun. So somewhere along the line, neutrinos are being quote unquote lost between the sun and Earth. And no one's really sure what's going on. Why are we losing them? How are we losing them? But the solar wind is what would carry those from the sun to the Earth, and that wind is produced in the corona. And I think you have a picture here. That's granulation. So here's our total solar eclipse picture. And this bright white mass that you see around the sun, this halo, that's the corona. If you look really closely, you can kind of see there's a colored flash around here, and that would be the chromosphere. You have to get really close on this thing, though. I don't know if you can kind of see, and it's almost, I have to wonder if that's an artifact of the camera, or if that's really the chromosphere you're seeing, this kind of reddish limb around the sun. This is from the ESO.org. This is the European Space. Sorry, I don't think that's what that is. European Space Agency is ESA. So I don't know which one this is. Sorry. So that's our total solar eclipse. That's the corona with the chromosphere. And then there's another part called the heliosphere, which is not always included in the description of the solar atmosphere. But this is just kind of the magnetic field, kind of the solar wind. It extends to about 20 solar radii. So it gets about 0.1 AU. So it's only about a tenth of the way from the sun to the Earth. And it's just kind of the rest of the atmosphere of the sun. But you may hear people talk about the heliosphere, especially if they're going to talk about the Earth's magnetosphere, because those are the two that are going to probably interact. But you don't always see heliosphere as part of the structure of the sun. All right, so that's kind of our basics of the structure. Now we're just going to talk about a few of the kind of fun things that go on in the sun, which we mentioned a little bit already. So sunspots and solar storms. So sunspots are regions of very high magnetic activity. So you'll see them as dark spots on the sun, which I think we kind of saw that on our images of Soho, from Soho. So here's our picture of the sun in the visible light, and these dark spots are the sunspots. And they're dark because they're cooler, because the magnetic flux from the magnetic fields, entering and coming back into, or entering and exiting the sun, that flux inhibits convection. Remember, convection was how the heat is coming up to the center, or from the center to the surface of the sun. And the magnetic field inhibits that convection, so it reduces the temperature. So cooler temperature looks darker on the surface to us. So the magnetic fields can get kind of tangled and twisted and produce what's called a solar flare. And again, part of that tangling is caused by the differential rotation of the sun. So over here we have there's a bit of a animation here of a solar flare actually erupting. So right in the center here, that bright spot is the solar flare. And then you'll see off on the edge of the sun here, there's a big, huge loop that comes up and off, and that's a prominence. Prominence and flares are basically the same thing. Solar prominences are usually just bigger, and they're seen edge on, like this one in this kind of animation that's going on here. That big, huge loop that comes off. You can see it right on the edge of the sun. So sometimes these flares will result in what's called a coronal mass ejection, or CME. And so it's this massive plasma that's exploded into space, and that radiation can actually reach the Earth and really affect our electrical systems here on the planet, and it will also produce the northern and southern lights, the auroras. I think just recently there was, we had a really big magnetic or geomagnetic storm, and I don't remember, I think it was just a couple weeks ago, but supposedly you were able to see the northern lights as far down as Georgia in the United States. And normally, I don't even know if they get to Minnesota. Sometimes I remember people be like, oh, you can see them in Minnesota, but it was not that often. Usually it's contained mostly to like the polar regions. So when it got down to Minnesota, Wisconsin, it was kind of a big deal. It gets down to Georgia, that's a huge deal. And that was because there was this huge solar flare that erupted that actually reached Earth, and when it interacts with the Earth's magnetic fields, all that material from the sun ionizes and produces those northern lights. And the stronger the solar flare, the stronger those auroras, and the particles travel farther down the Earth's magnetic field before they actually ionize and dissipate. So it was so strong that they stayed in the atmosphere until they reached all the way down to our southern latitudes, which doesn't normally happen. Normally they ionize, they dissipate up there in the polar regions. So that was pretty cool. I think it was supposed to be visible here in Iowa, but it was probably too cloudy, because if you're from Iowa, you probably know that, you see the sun for a couple months of the year when it's scorching hot, and then kind of disappears, so you don't see anything for 6, 8, 10 months. Why do we like living in Iowa? I'm still trying to figure that out. Anyway, so I missed that solar storm, that Northern Lights show, but that's what the Northern Lights are caused by, is this interaction of from the sun's solar wind and the Earth's magnetic field. So let's see. So the most common strength scale for these CMEs, or these solar storms, it's a G scale, and it's used by the U.S. NOAA, National Oceanographic and Atmospheric Administration. So it's a G1 through a G5, with G1 being the weakest. And there's some different scales I saw. There's a K scale, or K index, and A index. Most of the time you'll see it's a G5 or a G1 storm. So the strongest recorded storm in history was in 1859, called the Carrington event. And in this event, telegraph wires actually caught on fire. So there was a solar flare that was so powerful. It was a direct hit to the Earth, because a lot of times we have these solar flares that are very powerful, that are erupting into space. They're just not they just don't reach Earth. We're not in the direct line of fire of these solar flares. They're being ejected off in different directions that aren't going to hit Earth. So it just happened with this Carrington event, and they think that there may have been two of them, to kind of, the same direction. You got these kind of two impulses of very strong material coming at the Earth. And it was enough that telegraph wires caught on fire. And that's been the strongest ever recorded. This last one, though, that I was talking about, where we saw the Northern Lights in Georgia, that was supposed to be pretty strong too. I thought they said it was going to be a G5, but I don't know. They always say it's going to be the worst case scenario, and then it never is. But this last one was pretty strong, was my understanding. But that's why it's a big concern with a lot of solar astronomers, that you kind of study this thing, you kind of see that this happens all the time. It's just a matter of time before we are in the line of fire from a solar flare, and it can really destroy our electrical grid. So there's always kind of this push for hardening the electrical grid in our country so that we can withstand a solar flare, a magnetic storm like that. So the next thing to talk about will be the solar cycle. So every 11 years, the sun's magnetic poles flip. So the North Pole actually flips and becomes the South Pole becomes the North Pole. And it does so to make a full, complete flip and then go back to normal. That'd be one complete cycle. That would be 22 years. So every 11 years, the poles flip, and then 11 years later, they flip back. That's a full cycle, is 22 years. So we're currently in solar cycle 25. The Carrington event happened in solar cycle 10, and that was 1859. So I think they've been recording solar cycles since like the 1700s, I thought. So we're in cycle 25. It's started in December of 2019 and is projected to go till 2030. So the solar cycle affects the solar activity and the sunspots. So at the beginning of the cycle, the magnetic field is the weakest, and sunspots are pretty few in number. And then mid-cycle, your magnetic field increases, it gets stronger, so your sunspots grow and increase in number till they reach a maximum. And then again, it goes back as it flips back. Magnetic field weakens, sunspots become fewer. And let's see if I've got... So here's a graphic of solar maximum and solar minimum and the sunspots. So on the left we have solar maximum, and you see the sunspots mostly occur at the northern and southern latitudes of about 30 degrees, north and south. You have a lot of sunspots at solar maximum. And again, this is because of the differential rotation, that you have them at the 30 degree mark. And then at solar minimum, basically you have no sunspots or very few sunspots, and when they do occur, they're going to occur at the latitude or at the equator. All right, here's our European Space Agency. This is the one I was trying to garble my way through before. So they've got a picture of the sun from each of the years in their solar cycle. So this is a period of about 10 years, starting 1996. So the darker the sun, the cooler it is, the less active it is. So whenever you see a bright spot on this image, that's going to be a sunspot with a magnetic field. So 1996, it's fairly quiet, fairly dim. There's not a whole lot going on. You can see there is a bright spot near the center, like we would expect. And then it sort of increases in activity. 1999 is pretty active. 2000, 2001, you can see all your sunspots very close. They're kind of here in that northern latitude, that 30 degree mark. You do have some around the equator. So 2001 would be kind of your midway through that 11-year cycle. So we only talk about the 11-year cycle because it's the flip. Some people talk about the entire cycle because a flip you're kind of going from normal to flip to normal as a full cycle. That's the 22 years. But most of the time we're not going to talk about that. We're really just interested in the normal and then flipped 11 years. And that's really all we care about. Because then it's just going to be the same thing but in reverse. So then here we have, 2001 is our kind of our peak activity, and then you can see it kind of starts to dim back down. 2004, we're starting to kind of get the sunspots just at the center, at the equator. 2005 looks, kind of similar. Then 2006, we're kind of back to almost a very dark, almost black sun. There's very little activity in 2006. So that's kind of a neat visual image of the entire 11-year cycle. It's 10 years here. Again, as pretty much everything in astronomy, it's all kind of approximate. There's always going to be some variation. Maybe it's 10 years, maybe it's 12 years, but on average, it's going to be 11 years. And then the last thing that I would like to talk about is eclipses, which we kind of already touched on that, so we'll just kind of see if there's any. That's our picture there. Here's our eclipse. So the most recent one, as you may know, was this past April 2024. So it was seen across much of the United States. And the last time we had a total solar eclipse visible in the US was also in April, and that was in 2017. And I think I heard everybody talk about how rare this is, and solar eclipses happen like twice a year. So to me, that's not very rare. But, and I don't know if I didn't really pay attention to the kind of hype surrounding the eclipse this past month or a couple months ago. Maybe they were talking about the fact that it's happening again in the US, because normally you don't get total solar eclipses in the same place that close together. Usually it takes about 375 years for a total eclipse to happen at the same place. And in 2017 and again in 2024, most of the US was seeing a total solar eclipse. Again, if you weren't in Iowa, because it's always cloudy here, so I actually did get to see it though. I got to see, we had a partial eclipse here in Iowa. We didn't get to see the total, but it was a pretty decent partial, and you could actually, as I'm sitting at the table, it actually did get dark, which was pretty cool. I mean, it's just the moon is passing in front of the sun, and it actually darkens it noticeably. Here's the other cool thing that I like about just our solar system setup, is that the moon is just the right size at just the right location to be the same size as the sun. I mean, it just seems like, how does that happen? That it's just the right size to cover the sun and produce the eclipses. And I didn't get into the history of it this time, but I mean, eclipses have always been seen as like omens and kind of signs from the gods. That's, either something good or bad is going to happen, probably something bad. Because, I mean, it gets dark in the middle of the day. I've heard that nocturnal animals will actually come out because they think, oh, it's dark. It didn't get that dark here this time, because again, we were only a partial, but I actually did get my solar eclipse glasses out and looked at the sun. So that was pretty cool. But yeah, so usually, total solar eclipses don't happen in the same place very often, but we have had several here in the United States in like this less than 10 years. So that's pretty cool. So eclipses can only occur during the new moon phase, because it's the only way that the sun and the moon will be lined up so that the moon can actually pass in front of the sun. Any other phase, the sun and moon won't be lined up to cover each other. It can only happen during the new moon. Most years only have 2 solar eclipses, but we can have up to 5 according to NASA. And this did happen in 1935. We had 5 solar eclipses in 1 year. And it's supposed to happen again in 2206. I don't think any of us will be around, but maybe if you have some sort of avatar projection of your consciousness, you can hang out and wait around till 2206 and see if you can watch all 5 solar eclipses. Now, we do have lunar eclipses quite often, like those. That's not unusual. It's still cool, but they're not as rare. And eclipses often happen in cycles. It's called a Saros cycle. So roughly every 18 years, you'll have an eclipse cycle. One last thing about eclipses is that they often happen over the ocean. So a lot of times it may seem like we don't have eclipses that often. A lot of times it's just because we just don't see them, or we can't see them. So there's this website called dateandtime.com, which I like to go to for all the eclipse information. They have really a lot of good information about eclipses on this page. So here they've got their 5 upcoming solar eclipses. So the next one, October 2nd, 2024. So you're like, oh, cool, we've got another one. But if you look at the picture of where it's going to occur, as I just clicked past it. So the eclipse shadow pass, so the darkest blue stripe here is the total eclipse. And then the lighter blue areas are partials. And for the most part, it happens out in the Pacific Ocean. A little tip of South America is going to see a total eclipse. But for the most part, it happens out in the open ocean. And that's what happens with a lot of eclipses. I mean, the Earth is mostly water. So that's usually where the eclipses are going to happen. Let's see here. We got another one. It says March 29th, 2025. That's a partial. 2026, here's another full. But you see kind of where it's going to be is essentially, up close to Antarctica. So you're not really going to see. There'll be a little bit, down in the very southern portion, even southern from Australia. Again, out in the ocean. So we just don't see the solar eclipses. That's why I think people get a little bit weird when it happens in the same place. Like I said, the U.S. had these 2 total eclipses not too far apart, within 10 years. So, and then I don't know if we've had partials. I should keep better track of them, but again, a lot of times I just get disappointed because I'm like, oh, it's very cloudy where I am, and I'm not going to drive 3 and 4 hours to go see it. I mean, I love the sun and I love astronomy in our solar system, but am I going to drive 3 hours to go watch it? Probably not. I'll just watch it on the old internet. All right, so this is a good site to look at. They have a lot of, like I said, good information about eclipses in general. So, timeanddate.com. I'll put all these in the show notes. So, guys, that's going to be it for me. That's the sun. Obviously, I didn't get into a lot of the very technical details, which we can do later, but I think I'm kind of droning on here as it is. So I think we'll just call this good. And if you guys have any questions, comments, if you want to hear about any specific topic, let me know. Again, you can go to the website. There's the contact form. You can find me on Instagram, Facebook. Don't use Twitter. I'm not really on there. I have the account, but I don't ever check it. So email, contact form, Instagram, and Facebook would be the places to find me. And I'm going to see about doing a Facebook group. I have a group page for the interested reader, but I think I set it up wrong. It's really hard to find and nobody can find it, and it's bizarre, so I'll have to rethink that. But I do have a personal Facebook page that you can contact me on. I think all that's linked on, I don't know how it's linked on the website. I should probably know these things about my own website, but personal Facebook, you just look me up as Sarah Tyke. I think there's only one of us on there. All right, so let me know what you guys are thinking about. Let me know if you have questions, whatever you want to talk about. All right, well, thanks for listening, guys, and I will see you again. I'm going to try to, I don't think the 2-week time frame is going to happen, so we'll plan for one. I hate to even say this. We'll plan for once a month for the podcast for now, just until I can kind of get some stuff straightened out for my other business side of this. But yeah, so I'm trying to post fairly regularly on Instagram, Facebook. So if you want to go there for updates, that's probably the best place to find me. So, all right, guys, thanks for listening, and I will talk to you soon. Bye. I hope you enjoyed this episode and are inspired to question and investigate the world around you. Let me know what you're thinking about. You can contact me through the website, theinterestedreader.com, send me an email at sarah@theinterestedreader.com, or join the Interested Reader group on Facebook. I'll see you at some later time T, where T is greater than T naught, and T naught is equal to now. Thanks for being an interested reader, and I'll see you next time.